Okay, so this slide compared the analogy between the electrical field due to charge distribution and magnetic field due to current distribution. So first, let's check up the point source. So this is point charge, and this is point current source. So we see the magnitude of E and H field are similar. They are inversely proportional to the distance r, and they are proportional to the source strengths Q and I over here. And however, the difference is the direction. The electrical field direction is is aligned with the line between the observation point and the source, while the direction of magnetic field is orthogonal to the direction of the line between the source and the observation point. And here is the result of infinitely long line charge and infinitely long line current. So here is the source placed along the z-axis. And as you can see, the electrical field is pointing to the right, and its relationship is inversely proportional to the distance r. And for the magnetic flux density, the magnitude is also inversely proportional to r, while the direction is pointing this way, which is perpendicular to the AR direction. So there's relationship, but the relationship of E and H field due to line charges or line currents are similar, but they are not exactly the same. So next is the result of infinite plane source. So to the left is infinite charge plane. To the right is infinite surface current. So the red arrow indicate the direction of the electrical field and the magnetic field. So again, the electrical field is aligned with the AR direction, while the B field, the B magnetic flux, is perpendicular to AR direction. So again, they are similar, but not the same in terms of direction. In terms of direction. 讲英文的时候，有的时候就会卡到哦，不好意思。All right, so next let's look at the biosapphire law in a slightly different way, because in the original formation of biosapphire law, oh no, it's not biosapphire law, I'm sorry. In the original formation of magnetic force, we are looking at the force due to current source. The new formation as shown in equation 1.83 is finding out the magnetic force from the perspective of a moving charge. So as you know, the current can be regarded as a collection of moving charge, or a fast-moving charge can be also regarded as a current. They are related, but they are, can you call that the two are the same? Well, not exactly. But anyway, I will tell you the difference along our study of electromagnetics. But here's the expression, but that I guess you already know, that F equals to QVB, right? In your high school, you probably already tried to memorize this equation for the magnetic force F equals to Q times V times B. But by that time, probably didn't take into account of the direction. So it's actually QV cross B. V is not voltage. V is what? V is the velocity of the moving charge. B is the magnetic field. So as you can see here, we begins from B, dF equals to I dL cross B. dL is a short distance. I is the current of the line source. B is the magnetic flux, and cross products suggest the magnetic force experienced by this short piece of current. If we imagine that this short piece of current is produced by a moving charge, which has a charge density of Q and a moving speed of V, then I, the current, can be found as dq over dt. dq over dt. The time varying charge is equivalent to current. The next thing is dl. dl can be imagined as v times dt. V is the velocity. The velocity times time, dt, a short period of time. V times dt equals to the distance moved in this short period. So it can be replaced with, so dl can be replaced with dt. So if you do the two replacement, then the dt in the denominator and numerator cancels. So you end up with dq times v cross b. So be sure that you take the cross product here. So you have the cross product of the two vectors v, the velocity of the charge, of the moving charge, where the charge amount is dq. So it's a small charge, a small amount of charge. And this charge is moving in the background of a magnetic field. So B is not produced by the moving charge. It's not produced by the current. B is the background magnetic field. So this will tells you that if you have a moving charge moves into the neighborhood of with magnetic field, then this moving charge will experience some magnetic force. Okay, I remember last week I mentioned the 微中子吧，对不对？好，那说为什么微中子没有办法被侦测？因为它不带电，所以你没有办法用电磁力的仪器来去侦测它。但是对于大部分的宇宙射线来讲，你可以用电磁的侦测器来去侦测它。那用的其实就是这一个关系哈，当你这一个快速移动的高能粒子进到一个准备备有背景磁场的环境的时候，你就会发现它受力。那有受力的话，就比较容易被侦测到啊。Alright, so this new relationship that specify the magnetic force from the perspective of moving charge can be written as F equals to QV cross B. Okay, so remember the cross product. This shall give you a more complete sense about the magnetic force. All right. So what happens? what happens next? If you have a charged particle moving in the presence of a magnetic field, what happens? Well, it has the magnetic force acting on the charge, acting on the moving charge. And the force, what happens with what is the result of the force? Well, the force will change the velocity of the moving charge. Agree? Oh, it will, well, F equals to what? M times A. Oh. F equals to the mass times what? Acceleration 啊，加速度乘质量等于你的受力嘛，哈，所以这边是受力，那我们这边看到的是 F 等于 QV cross B 啊，所以，你可以找出这一个 ，you can find out the charge, the force, the acceleration, acceleration due to the presence of magnetic force. However, because F is a vector, so it has, in fact, has three unknowns. Because F have a projection on X and Y and Z. So with the knowledge of F and the moving velocity V cannot provide you the total solution of the whole solution of B, because F is acting on a specific direction, which is B times sine delta, where delta is the angle between velocity, charge velocity V, and the magnetic field B. So to find out the representation of B, we must determine the maximum force, which is QVB, that occurs when delta equals to 90 degree. So, and how do we find this? You can try out several directions of V to find out the maximum acceleration or maximum force. Okay. So if the maximum force, say Fm, can be found, then it occurs at you can find out B with this relationship, that is taking the cross product of Fm with Am, that is the direction of the moving charge, and divided by QV to find out the magnetic field, magnetic flux density. Okay, so B can be rewritten as equation 1.86. So for a very small charge, that is Q goes to 0, then the amount of magnetic flux density can be found by Fm cross Am divided by QV. Okay. So what happens for this magnetic force? Interestingly, for electrical force, for a charged particle, if you experience electrical force due to the presence of electrical field, because the electrical field direction is along the direction, is acting directly on the charged particle. So the F, the electrical field will increase or decrease the magnitude of velocity of a charged particle. On the other hand, because the magnetic force due to the magnetic flux density in the background is acting on the direction perpendicular to the moving direction of the charge. So it will change the velocity of the moving charge, but will not change it will only change the direction of the velocity of the moving charge, but will not change the magnitude of velocity of this moving charge. So this is a very important difference. 电场作用力可能去改变受带电粒子在电场中的速度大小，也会改变它的方向。因为电场作用力的方向比较明确了哈。但磁场作用力的话，因为磁场作用力的方向永远跟带电粒子运动的方向 v 是正交的，所以那个作用力会改变它的速度。但是它只会改变那个速度的方向，而不会改变速度的大小所以对于磁场作用力还有电场作用力对于带电运动中的带电粒子的影响，请你要分清楚电场作用力可能改变速度的大小跟方向，而磁场作用力只会改变速度的方向，不会改变速度的大小因为磁场作用力的方向跟移动的那个速度方向是永远正交的So here's an illustration. In this figure, we see a charged particle moving upward with a speed of v, and in this scenario, you only have magnetic flux density b pointing this way. And use your right hand, you can find out the direction of the force. Say at this point, the direction of magnetic force is pointing to the right. If you are looking at this position, the direction of magnetic force is pointing down. If you are looking at this direction, the magnetic force is pointing to the left. So it's always perpendicular to the direction of movement of these charged particles. So it will only change the direction of the moving particle, but not change the magnitude of the velocity. So if the background is, if the charged particle is injected to this environment in this fashion, that is perpendicular to the direction of B, then it will actually circling around this plane, due to the presence of its of its velocity and the presence of the background magnetic field. So the force, which can be referred to as 向心力还是离心力，到底是哪一个对的？Centripetal force. Centripetal force, according to Newton's law of centripetal force, that equals to mv to the square over r. R is the distance of the circular movement. And you can take in the equation, that is, when the centripetal force is the same as magnetic force, the radius of the circular movement r, the radius r of the circular movement can be found as mv over qb. So once you know the magnitude of background magnetic flux, the charge of the charged particle, the mass of the particle, and the velocity of the particle, then you will find out the radius of this circular movement, or vice versa. Once you know the radius of the circular movement, you can find out the ratio of m over q. So this is the principal mechanism for mass spectrograph, 质谱仪mass spectrograph. That is to find out the mass to charge ratio, that is m over q, of certain particles, So it's changed the velocity of this charged particle so that it can, put it a simpler way is that if you can make the charged particles move in a circular fashion, that is, to have this particle, this charged particle goes through this curvature area with specified radius, then you know the mass to charge ratio, m over q. So this slide, this slide explains some of how it works for the mass spectrograph. Okay, so due to the timeliness of this lecture, I will leave up to you. Okay. So here's the result. The distance, the rate of circular movement r can be found by square root of 2 times v. V is the this is not the velocity, sorry. V is the voltage for the acceleration of the charged particle. B is the magnetic flux density of the equipment in the background. And the unknown that we want to find out is m over q. The mass to charge ratio. Okay. So of course, as you already know, mass spectrograph is very important to the study of material, to the study of chemistry, so that we can determine the formulation of specific molecules, we can find out we can confirm the structure of a certain substance. Okay, so next we move on to our last topic of chapter 1, that is Lorentz force equation. So combining the two forces, that is the electrical force and the magnetic force, we can form equation 1.89, which is referred to as the Lorentz force equation, Lorentz force equation. So it's simply the summation of electrical force and magnetic force. So if we write it in terms of charged particles, then it appears to be QE plus Q times V cross B. Okay, so V is not voltage, V is the moving speed of the charged particle. Okay, so if the charge is static, if you have a static charge, it will only experience electrical force in the background. On the other hand, if you have a moving charge, then if there are electric and magnetic charge in the background, it will experience both electrical force and magnetic force. Right. So the amount and the direction of the electric and magnetic field can be determined by some test charges, by injecting the test charge at a different speed or different directions. So for a given B and E, for a given B, E can be found from the force of one velocity because FE acting in the direction of E. So according to this description, it's easier to find out the electrical field in the background. On the other hand, for a given E, B can be found from two forces for two non-collinear velocity. What is non-collinear velocity? 非平行的那个方向了哈，所以你只要测试背景的，你只要决定背景的磁场的话，你的那个 test charge 要从不同的方向打进去了哈，或打不同的那个速度，不同的方向，速度它的移动方向要不同了哈，才有办法知道。 because the magnetic force acts perpendicular to both V and B. So it cannot be determined with just one equation. It needs two equations. So if you do not know both electrical and magnetic field intensity, the knowledge of a minimum of 3 forces is necessary. You need at least 3 tests to find out both E and B. So here is one example. The force experienced by a test charge Q for 3 different velocities at a given point, in a region of electric and magnetic field are given below. So in this case, we do not know the direction and magnitude of electric and magnetic force. So however, we complete 3 tests. Test 1, we inject the charge Q in V1 velocity, which is V sub 0 in AX, in the AX direction. Test 2, the magnitude of, for test 2, the velocity is V sub 0 as well, but the direction is changed to AY. Test 3, the magnitude of the velocity is V sub 0 and the direction becomes AZ. So you use 3 tests of different directions to estimate or to find out the the background electric and magnetic field. Okay, so here are the, well, you will have homework problem in here, and here are the steps. So first, write up the force equation, then you do the use some linear algebra to simplify the problem, and use the cross product relationship to find out the solution, and substitute the part of the result to find out the magnetic field and electrical field as well. So in this case, we try to write up the equation in terms of Lorentz force, that is QE plus V cross B. And to the right of the equal marks are the result. So in the problem it says that test 1 ends up with force in this fashion. Now the amount of the force is QE sub 0 and the direction is AX direction. Test 2 give you this result, and test 3 give you this result, so they are somewhat different. And you do some algebra with the 3 equations. You have 3 equations, so you are supposed to solve 3 relationships. So do the substitution, do the algebra, you can eliminate E in the equations above, so you end up with these 2 relationships. Okay, so what next? What is the unknown? The unknown in these 2 equations is B, the magnetic flux. How to find out B over here? Well, you know, our knowledge to this problem is that the end product, the result to the right is perpendicular to B and perpendicular to the first vector as well. The end product here is perpendicular to B and perpendicular to the first vector over here. But anyway, you have 2 vectors that is perpendicular to B. So what you can do is taking the cross product of these 2 vectors to determine the direction of B. Okay? So because AX plus AY is perpendicular to B, and AX is perpendicular to B as well. So if you take the cross product of the 2 like this, then B direction will be in parallel with the new vectors, orthogonal. So do the cross product over here. You find out that B is in the Z direction, with an unknown constant C over here. So the magnetic field is pointing on the z direction, or minus z direction. Okay, so next is substitute this relationship that is replacing b with minus caz into this equation so that you can find out the exact representation of b. So be sure to do this yourself. Substitute the known relationship to find out b as E sub 0 over V sub 0 and the direction in the z. Alternatively, the textbook shows another way to solve this problem by assuming b as bxx plus byay plus bzaz. So it's a more, well, it's an alternative way to think about this problem. You just put the bxx, byay, bzaz into the relationship and try to solve for the three unknown bx, by, and bz. So check out by yourself. You can find out that using this approach, you will find that bx equal to 0, by equal to 0, and bz equals to E sub 0 over V sub 0, which is the same as the first method. All right, so here's the example for the calculation or the application of Lorentz force. So the Lorentz force can determine the speed, the movement of a charged particle with the presence of electromagnetic field, right? Oh, so sorry, that's the last step. Okay, I didn't complete the example yet. So in the previous slide, we already find out the representation for B. Then the final step is substitute the representation of B into the Lorentz force so you can find out the solution for electrical field. So this is the complete solution of the example problem. And so before we end today's lectures, we may discuss a little bit about the importance of Lorentz force. Lorentz force is so important. Otherwise, there will be no Professor Liao here and will be no you. There will be no life on Earth. Many believe that once there are lives on Mars. However, if we go to Mars right now, we may find some traces of lives in the past on Mars. Even though that we have already found some ice sheets on Mars, okay, there are reports that confirm that they may have some ice sheet on Mars, and there may be life under or biomechanisms underlies the ice sheet. And if Musk to successfully bring the human beings to Mars, at the first few decades, life on Mars shall be rather harsh because you cannot live on the surface of Mars. At the first few decades, you must hide yourself underneath the Mars surface. Why? Because the presence of cosmic rays, that is, high speed or high speed moving particles in the cosmos, in the universe. Fortunately, on Earth's surface, the density or the intensity of cosmic ray is relatively small comparing to Mars. Why? Because Earth is because Mars is dead. Because Mars do not have a magnetic field. Okay? Similarly, the Moon do not have magnetic field. On the contrary, Earth do have magnetic field. You can imagine, or in theory, the magnetic field on Earth is produced by what? Partly because we have many liquidized iron in the middle of Earth. So, as you can imagine, it produces magnetic field around the Earth. So, if you have a charged particle Q coming this way, what happens? This charged particle will be, the moving direction of the charged particle will be changed due to the presence of Earth's magnetic field, B. So V cross B, it will circling around the Earth's surface. So instead of hitting the Earth's surface directly, charged particle, the fast-moving charged particles will be moved around the Earth's surface to the back. So if you check up the distribution of charged particle around the Earth's neighborhood, you will find out, okay, so this is the direction of the sun. Most of the fast-moving charged particles are produced by sun, as you can imagine. Okay, so the charged particles are found near the Earth's perimeter, but not much less on the Earth's surface, due to the presence of magnetic field, Earth's magnetic field. So what happens if those fast-moving charges particles hit the Earth, hit your body? What happens? It will increase the chances of getting cancers, because those fast-moving charged particles is referred to as